Welcome to lecture 7.3, where we shall discuss computational aspects of continuous wavelet transform. In the previous lecture, that is 7.2, we learned how to convert scale to frequency and the philosophy surrounding it as well as the procedure. The reason for discussing the conversion from scale to frequency upfront is because in CWT as well as in scaleogram, those points as well as the procedures will come very handy. In this lecture, we shall specifically focus on two algorithms for computing continuous wavelet transform. One is the convolution algorithm and other is the fast Fourier transform based algorithm. These are two different algorithms, the transform remains the same, and we shall also demonstrate how to compute these how to compute the CWT using these two algorithms in Matlab for you on a couple of examples. So, just to recap, the theoretical definition of continuous wavelet transform as given in equation 1 here, you can recall from lecture 7.1. It is nothing but the transform of the signal with the wavelet at that scale and that location tau or the translation parameter tau. And also we had given the expression for synthesis or recovery of the signal, and this recovery is possible only if the wavelet satisfies what is known as an admissibility constant condition, that is this constant C psi should be less than infinity, it should be bounded, it should be a finite value. On the other hand, for analysis the wavelet should be of 0 average, and from a functional approximation viewpoint recall that this should get you the local details of any signal, or from a signal processing viewpoint this is a requirement for the wavelet to act as a band pass filter. Now, both these conditions, that is the one for analysis and recovery, are more or less equivalent, because for C psi to be a finite value, the magnitude square of psi of omega, although I write this as psi star of omega times psi of omega, there is a reason for writing it that way, which will become clear when we talk of inverse CWT in a later lecture. So, the magnitude square of psi of omega should decay faster than omega, so that C psi is constant. The other way of looking at it, in fact, a more strict requirement is that the Fourier transform of the wave or the wave, at omega equals 0 should be 0, because we have particular difficulty in evaluating this integral at omega equals 0. That is where we run into the singularity point, and to avoid that difficulty, that predicament, we want to have the psi of omega to be 0. When that is the case, then we do not run into any issues. Requiring that the Fourier transform of the wave to be 0 at 0 frequency is the same as saying that the wavelet should have 0 average. That is by virtue of the property of Fourier transforms, where we know that the value of the Fourier transform of a function at 0 frequency is nothing but this integral that you see in equation 3. So, now we will talk about the main topic in this lecture, which is computing the CWT. And as I said earlier, we are only going to talk about the forward transform, the inverse transform, that is the recovery, shall be discussed in a separate lecture. So, the first algorithm in the list is a convolution algorithm, which is based on the convolution interpretation of the continuous time wavelet transform. This was discussed in lecture 7.1, if you may recall, where I could write the wavelet transform as a convolution of x with psi bar, and psi bar is nothing but a reflected version of the wavelet. It is no different, it is not something starkly different from the wavelet itself. And in practice, what we do is we replace this theoretical convolution with a discrete version, because I work with finite length data, and therefore, I have to implement a finite length convolution. And this convolution expression that I have given in equation 6 is not in the standard form. In the standard form, you would have had psi star of n minus k times Ts, but here I have k minus n Ts. So, let us take some effort in understanding the new quantities that have been introduced in this expression. The big N is of course the length of the signal, and the small k keeps track of the sampling instant, and the small n is a dummy variable. Sorry, it is not a dummy variable, k is the dummy variable. The small n keeps track of the discretization in tau. We said that the theoretical convolution has to be replaced with a discrete version, but at the same time tau and s are continuous valued variables. I cannot compute CWT over a continuum like the same arguments that we gave in arriving at DFT. I cannot compute DTFT over a continuum of omega. Therefore, I discretize omega. Here I discretize tau and s. So, the discretization of tau leads to this grid on tau, and n helps me keep track of the grid point, and the discretization of the scaling parameter leads to a grid on the scale axis, and m helps me keep track of the point on the axis corresponding to scale. So, n and m are essentially the discretized versions of tau and s, and t subscript s, the big T subscript s is a sampling interval, and once again s subscript m is the value of the scale at the mth grid point. So, that is it. So, we have essentially completely discretized equation 5 so as to suit the practical situation. Now, if we were to summarize the, or if we were to list the steps in the computational algorithm based on this convolution expression, it would be as follows. Step 1, what you have to do as a user, specify the grid of scales over which you would like to compute the CWT. That is important because the algorithm needs to be told that. So, you pick the first point on the scale grid, and for that you compute for the entire set of tau points that you have discretized. So, you start with the first grid point on S and set tau equals 0 because that is the first grid point on tau. Compute the convolution as given in equation 6. Now, increment tau according to your choice, that is in tau has units of marching in tau amounts to traversing the wavelet along the length of the signal, and there you have freedom in how you want to march ahead. The default that is used in many algorithms is n equals 1, that is you will march in the same time step as the signal itself, that is tau will be incremented by Ts, a sampling interval. That leads to a highly oversampled continuous wavelet transform, a very dense one, which is okay, it is good for feature extraction. So, typically n is set equal to 1, but you could choose otherwise. In discrete wavelet transform, for example, the marching in tau is not done this way, it is done, the marching in tau depends on the width of the wavelet at that scale. If you have a wider wavelet, you will have fewer points on the time axis to march. If you have a narrower wavelet, you will have on a finer grid. So, here this is how you increment tau, and then keep repeating steps 1.1 and 1.2 until you have reached the signal, and repeat this step 1 itself for every grid point on the scale axis. So, that is it. So, you have 2 loops, one for the scale, one for the tau. So, therefore, you should expect this algorithm to be computationally intensive. So, let us look at a Matlab based example in computing the signal that has 2 frequencies running in parallel. So, it is as if 2 sine waves are superimposing on each other. What I show you here is a magnitude of the CWT. The wavelet or the mother wave that I am using to compute this transform is C mod wave f, and the routine that computes the continuous wavelet transform using the convolution algorithm is CWT. So, the first 2 lines in this code essentially generate the sine wave. Now, the sine wave has 2 frequencies, 4 hertz and 15 hertz running in parallel, and the sampling interval can be computed here. Now, what I do here is I show you 2 different ways of doing things. In the first case, you pretend that you do not know the sampling interval, so you set it to 1. If I am given data and if I do not have an idea of what the sampling interval is, then I will set the sampling interval to 1. That is what I am doing here. Now, I will draw your attention to this command here that I have written, S naught equals 2 times Ts. What is this S naught? This S naught is the first the minimum scale at which you want to compute the CW. Now, scale has an inverse relation with frequency. So, the minimum scale will correspond to the highest frequency, and from sampling theorem I know that the highest frequency that I can detect in that is the highest continuous time frequency that I can detect in a sample signal is Fs by 2, where F is the sampling frequency, right. Fs is 1 over Ts, that means the highest frequency that I can detect is 1 over 2 Ts. Therefore, the minimum scale that I can start with is 2 times Ts, right, and that is the reason that I have 2 Ts here. Then the grid size is your choice. What I do here is I choose a dyadic grid size, but you could choose a linear discretization. This dyadic is keeping in mind that we will work with DWT in a few lectures from now. So, I choose here a certain grid size and I go up to the length of the signal. Based on the length of signal I choose my scale, maximum scale. Remember, the maximum scale corresponds to the lowest frequency. Ideally, I should not be even trying out log 2 of n, I should be trying even lower scales, because you may not be able to detect frequencies as low as corresponding to this maximum scale, but it is okay for illustration. Then I compute the CWT, I pass the signal that I have, discrete time signal, I also pass the scales over which I want to compute the CWT. I do not have to specify the translation grid, because as I said the default is given in CWT. It is assumed that you want to discretize tau the same way as you have discretized time for sampling x. And the wave, the particular wave that I want to use is a complex Morlet wave. Recall in 7.2 we have talked about the suitability of using complex Morlet wave for CWT. Then I convert scale to frequency again. For this, recall what we had talked in lecture 7.2, where we gave a table of theoretical conversion factors for scale to frequency, and I am using that for the complex Morlet wave, and I am essentially substituting that here, and then converting the scale vector to the f vec. The omega naught by default is set to 6. Strictly speaking, the CMOR wave f actually uses not omega naught equals 6, it uses 2 pi. So, the strict conversion factor should have been 6, not 6, but 6.28. So, you can try that out in your own leisure time. And then what I do is I plot a contour, I draw a contour plot of the magnitude of CWT with time on the x axis and frequency on the y axis, and the magnitude plot clearly brings out the presence of 2 frequencies. Now, observe that one thing that you should expect, the wavelets at will give you more smearing of the energy at higher frequencies, because they are highly localized in time, and by virtue of the duration bandwidth principle you should expect more smearing of the energy in high frequencies. So, this you can recall from the previous lecture, that is 7.1 that we have talked about. Therefore, as you proceed to higher frequencies you will see more smearing of the energy, which is what the situation is, whereas at the low frequencies the smearing is low. Now, you see that we have generated a sine wave of equal power. However, of course, what you see in the plot is not power here, still the magnitude of the wavelet transform should look, you would expect them to look the same in terms of intensity as measured by the magnitude for these 2 frequencies, but that does not seem to be the case here. But of course, now just what do you say, an artifact. What is happening here is the energy at higher frequencies is smeared over a wider band. So, if you were to collect all the energies, this is not the energy plot, but imagine that I was plotting magnitude square rather than magnitude, which is what is done in scaleogram, then you would be collecting all the energy in this entire band of frequencies. That would give you the total power, that is averaging across all the scales, integrating across all the scales will give you the power present in the frequency, because this is still a pseudo frequency. Likewise here, then you would be able to come to the conclusion that both sine waves are present with equal intensity. Again, this is not an intensity plot, and the coloring scheme can also be changed. Here I have chosen a global coloring scheme. Therefore, you see this kind of a plot, and because of the smearing you see that the lower frequencies are colored in red, and but that is because you have also a narrower smearing, whereas for the higher frequencies you have a cyan color. You could also choose to plot in with a coloring scheme that is scale dependent, right, in which case you will not be able to compare across scales, because at each scale you are choosing its own color band. So, you are normalizing at each scale. So, that option is also available. In fact, I invite you to really explore other options of CWT, particularly the plotting options, which I do not show here. This is the basic thing that you require. On the other hand, I would always recommend that you plot the magnitude of CWT by yourself to be really aware of what is happening, rather than just using some nice fancy features of any routine. Now, I said I wanted to show you two different ways of computing the not computing the CWT, but two different ways of looking at the same signal. The only difference between the previous version and this version here is I specify the sampling interval. Earlier I said I do not know the sampling interval, I will set it to 1. Now, I know the sampling interval, and what I do here is the same story. The minimum scale is set to 2 times Ts, but the syntax that I follow with the usage of CWT changes slightly. Earlier I passed the signal, now I am passing the signal as a structure. What are the two fields of the structure? The signal and the time vector over which the signal has been obtained. So, T vec is a time vector over which it has been obtained, and xk is a signal, and this is unfortunately this y and x are only because of the notation that is used in the routine. And I should also tell you that the documentation on the CWT in this release corresponding to 2014B does not really tell you how to pass the sampling points as well as a signal to CWT. This you will have to figure out by opening up the CWT code, and you will see that there is this option of passing the signal as well as the time points. So, I did that, and now I am passing the structure. What CWT does implicitly or within the code is it computes a sampling interval based on the time vector that you have given. And it is very important to do this, because the moment you set your sampling interval to this and you set your minimum scale according to the Ts, you have to pass on the time instance or the sampling interval indirectly to CWT. Otherwise, what happens is the scale that CWT uses is tied to the sampling interval, because you have done this here, right. Here you have explicitly put in an effort in setting the minimum frequency to 2 Ts, but the CWT routine also needs to know what it should do with the remaining scales, and therefore, it is important that you be consistent throughout. Once again I use a complex Morlet wave, and the rest of the story is the same. You should expect, of course, the two plots to be identical, the only difference being the y axis. In the y axis of the plot I had normalized frequency, which is the frequency of the discrete time signal, whereas here I have the frequency corresponding to the continuous time signal. And now it is easier to read. I know that the frequencies are 4 and 15, and the magnitudes reach a peak at 4 and 15. One point that you should observe, whether this plot or the previous, if you look at the magnitude of CWT, they are very small at the ends, that is at the borders, indicating or probably compelling you to believe that the signal really did not exist in this particular frequency, for example, did not exist in this initial portions, but that is not the case. We know that the signal exists right from the beginning, that is, this frequency component exists right from the origin and continues to through the end. So, why is this happening? Because of the border effects associated with convolution operation. All right. Now, let us look at the second part of the lecture, which is the computation of CWT via FFT. The idea is fairly straightforward. In the convolution algorithm, we took a convolution viewpoint of the wavelet transform. Now, what we are going to do is, we are going to take a Fourier transform of the wavelet transform. Now, that may sound intimidating to you or confusing to you, but we have done this before. We have taken Fourier transform of Wigner-Wille distributions as well. So, here I am taking a Fourier transform of the wavelet transform with respect to tau. The wavelet transform is a 2-dimensional function. I am only evaluating a 1-dimensional Fourier transform, and the dimension that I am looking at is tau. The basic idea is to avoid this this inner loop calculation in CWT, where I compute this convolution at each value of tau. With this algorithm, I compute the wavelet transform at a single scale in one shot for all values of tau. How do I do that? The Fourier transform helps me do that. The Fourier transform, 1-dimensional Fourier transform of the CWT with respect to tau is given here, root s x of omega times psi star of s omega, that again is by virtue of the Fourier transform property. And all I do is take an inverse Fourier transform of this to recover again inverse Fourier transform with respect to tau to recover the continuous wavelet transform. So, computationally what I do is, I take the Fourier transform of the signal and the wavelet, evaluate the Fourier transform of wavelet at s omega, obtain the product and simply take the inverse Fourier transform. And of course, in practice I have to implement a discrete equivalent of equation 7, and once again we have n and m taking the role of the discretized points on tau and s, and now x of omega is replaced with x of omega L, and psi star of s omega is replaced with psi star of sm omega subscript L. Of course, there is a root s factor which does not appear in 8. In fact, strictly speaking, that should appear here as a factor, but you could factor that into your psi if you like it. Okay. So, what is this omega L? Well, L is the grid point in frequency now, right. Like what you are doing here is you are replacing x of omega with its DFT and psi star of s omega with this DFT, and DFT works with discrete frequencies. This omega L is actually the Lth point on the frequency, discretized frequency axis. And of course, you have e to the j omega L n Ts, because taking the role of e to the j omega tau. So, that is what is happening here. Now, a couple of points here. One is that this algorithm is really beneficial in terms of computation only if you have an analytical expression for psi of omega, because if that is not the case, like in the Dobeschi wave and so on, then you have to go through this additional step of computing the DFT of psi. So, if you have a closed form expression, all you have to do is evaluate psi at that frequency Sm times omega L, and that saves the computation, DFT computation for psi. X of omega L, of course, you have to compute the DFT, there is no closed form expression for the signal xk. So, that is one point. The second point is that because that this algorithm assumes the signal to be periodic outside the observation interval. Why? Because I am using DFT, and DFT assumes the underlying signal which I have not observed, the infinitely long signal that I have not observed, to be periodic with the same period as the observation interval. Therefore, whenever you are using this algorithm for computing CWT, you have to watch out for border effects as well, where it is assuming that the signal repeats itself. So, let me show you a couple of examples. Again, we take the same 2 sine signal, but now I implement the FFT algorithm. The routine that implements the FFT algorithm is CWT FT, it is one word, and what you do here is as a part of the syntax, you generate a structure variable which takes the signal, which contains the signal as well as the sampling interval. Earlier we gave the time vector, but now we are giving the sampling interval, You could of course pass a signal itself directly to CWT-FT, in which case it will assume that the sampling interval is 1. So, that is the only difference. That is it. So, once I compute the Fourier wavelet transform using the Fourier transform algorithm, then I draw contour plot. Now, you can see, unlike in there are of course, a lot of similarities between what we have seen with the convolution algorithm, but one difference that you can see here is, if you compare we discussed this point, the magnitude plot seems to suggest that the signal is not present in the initial and the final portions, whereas the Fourier transform algorithm has not is not showing any such artifacts, because it assumes periodicity and so on. So, you do not run into this border effects really that you see in the convolution algorithm, right. However, let us take another example where I have signs in series. This is one of the classic examples that we have been using all along in this course. So, I have a lower frequency followed by a higher frequency occupying equal durations in the length of the signal. On the left plot, I show the contour plot of the magnitude of CWT using the convolution algorithm, and on the right hand side I have the same contour plot of magnitude of CWT using FFT algorithm. Besides the similarities, you should notice an important difference, which is that in the second plot here, that is the one that is computed by FFT algorithm, the lower frequency appears towards the end, whereas it, strictly speaking, we know that the lower frequency vanishes halfway through the time. Whereas in the convolution algorithm, I do not see the lower frequency resurfacing towards the end of the signal, and that is because of the different assumptions underneath these algorithms with respect to the signal outside the interval, right. FFT algorithm assumes that the signal is periodic, and because in the wavelet transform the lower frequencies have a much less smearing, you will see this coming in predominantly, showing up predominantly here. And whereas in the convolution algorithm here, I do not assume the signal to be periodic outside the interval, but it of course assumes something else. It assumes that the signal is, for example, 0 outside the interval and so on. Then you have no resurfacing of the lower frequency. So, in that respect, the convolution algorithm is better than the Fourier transform based algorithm, but it is computationally more intensive. So, it is always good to generate CWTs using both these algorithms and then figuring out what is the best algorithm for a given application. So, in this lecture, to summarize, what we have learned is the two different algorithms for computing CWT, and both these are coded in the Matlab's wavelet toolbox. You have CWT and you have CWT-FT. They run each of these algorithms with the necessary assumptions. We have gone through the syntaxes for the respective routines and also touched on the assumptions underneath these algorithms. So, there is no particular algorithm that one can recommend. Of course, from a computational viewpoint, the Fourier transform algorithm is much faster, but then it assumes the signal to be periodic. The convolution algorithm is computationally more intensive, but it does not make any assumptions on periodicity outside the interval. What we shall do in the next lecture is we shall study scalograms, which are computed from the CWT. So, therefore, this is an important precursor to the computation and discussion of scalogram, and here are a few references. I would suggest that you go through the Matlab's documentation on each of these algorithms and also work out examples, variants of the examples that we have presented in this lecture, also the examples given in the documentation, and come back to us with any questions that you may have. Thank you and see you in the next lecture.